Matt? Thumbs up.
It looks like we're going. Okay, the video's working. This shouldn't be too long unless it becomes long. I'm reviewing something that I've talked about before in these recorded meetings, but it's just a little bit more results and more summarizing it. So I have this write-up here that goes into detail about all of this. So therefore, I don't have to go deep into detail here, just tell you the broad themes. So it's called Achieving Sparse Connectivity. So what I'm doing is I'm taking a conventional neural network that has, input units, output units, multiple layers, and I'm taking the weights, and I am making the weight a computed value from as before, the network stores a bunch of weights for every connection, but it also stores a permanence for every connection. And in any particular time step, for any particular input, at least during learning, it will compute the weights by multiplying the weight that it's stored by this gating variable. And to really connect this directly to permanences, the whole thing works if you use this rule where if the permanence is less than 0.5, then the gate just zeroes out the weight. If the permanence is greater than 0.5, it lets it through. The weight, the connection exists. Now, for most of the results in this paper, I used an alternate stochastic version of it, where the permanence acts as more of a probability, where the synapse works with probability equal to theta. But this can work too. It just you have to train it a little different. You have to throw in some other kind of dropout, but it also works to do that. So this is like permanences in the sense that it's they're used in the same exact way, like during inference, for example, but they're trained a little differently. They're trained rather than being based purely on Hebbian, like this fired before this one. It's trained on whether the synapse was useful, on whether the synapse helped successful classification. And at the core, this is what I'm doing. We're hearing some danging from out there. So I've written about like how to do this, how to train these. There's a pretty straightforward way to do it that just involves passing the gradient through. It's a technique that has been used before. First place I saw it was a paper by Bengio. I derived it myself and then went and found where other people had figured it out before.
They did this same idea of using permanences?
No, they mostly used it for example, for binary weights, where a weight either exists or it doesn't exist. Mm-hmm. I've combined it with other weights so that I can use it as a sparsifying tool. Okay. So that's what I've done here. I've also experimented with the binary weights thing, and it works, but that just wasn't the task here. So now I'm going to show you two results. One, and then I'll talk about it in terms of the cartoon one. I'm going to scroll down. I talked about the model and everything. So on the left here, Google speech commands. Just to talk about these charts, I have accuracy plotted on the left. As you can see, I'm zoomed in way on like the 90-some% accuracies. And number of weights is on the bottom, and that's on a log scale. So moving to the left is a pretty dramatic sparsification, pretty dramatic reduction in cost. I'm plotting here. The blue thing is are my results, basically.
That means 100%? Is that?
Yes.
Okay.
Yes. That's where I'm not doing anything to try to make it sparse at all. Like all the
weights.
weights.
So you're talking over 2 orders of magnitude there too.
Yes.
Wow.
Yeah. And now these orange points are the HSD stands for how so dense. And there's nothing unexpected here. I think everyone in the room expects that when we go from this fixed sparsity network that we did in How Can We Be So Dense to a network that's allowed to change its sparsity where anything can connect to anything, you would expect better results. And so this is mostly just going to confirm our suspicion that if you allow this the dynamic rewiring where anything's allowed to connect to anything, then you can either achieve better results with the same sparsity or the same results with better sparsity or somewhere in between.
And that's what we are hoping for,
yes.
To get that. That's rather than just using static weights.
Yes.
It's like in our spatial pooler also. we train our permanences, and we can actually dynamically turn things on and off as well.
Yeah, so I don't think this is surprising, but it's just nice to see that it's working and we have at least one way to do this.
And that was like the main result I wanted to see.
Yeah.
Which means now you can get really sparse and hopefully maintain better accuracy than you could otherwise.
Yes. So that's pretty much, this chart is,
I mean, that comes from just having dynamic connectivity or dynamic sparsity.
yeah.
That doesn't necessarily come, does that necessarily come from using the
Permanence.
permanence thing?
Well, that's how I'm achieving this sparsity.
Okay.
So that's one way to achieve the dynamic sparsity. There are other ways to do it as well,
Yeah.
but this is the way Marcus is.
Okay, so I guess maybe that's an important question. Ultimately, is like, well, using permanences is one way. We like that. We understand the biology of it. Is that better than other ways, or I don't know, something like that?
That's still an open question for me.
Okay. Okay.
I want to compare this, for example, with something called a variational dropout. And also, they're just old techniques of just weight pruning. If you just prune all the low weights, how sparse can you get? Other people in the room. Okay. So really, everything I'm going to talk about revolves around these charts or the cartoon version of them. So here, I'm just showing the same thing where the dynamic version can do better than the static. However, I should point out that I don't want to talk this up too much. This is dense to sparse, where the training is fundamentally still a dense process. I am evaluating every possible connection in this network. So if something is sparse to sparse, if it's sparse the whole time, there's a lot more room for efficient training that I'm just not doing here. So there is this downside is
efficient meaning you could spend less time training.
Yes.
If you're doing sparse to sparse.
Yes. Yes, I went with the easy task first.
Okay.
Of dense to sparse. Okay. And so we especially expect, because I'm doing dense to sparse, we especially expect this line to be better. So you could imagine a sparse to sparse might be somewhere in between these, and we'd be trying to get it as far over as we can. That's at least what I would expect. Now, I do want to draw attention to the fact that that I don't know how unexpected if you the fact that dense networks still do get better results. It does involve giving up accuracy. Anytime we can get these order of magnitude improvements and costs, but it does involve giving up some accuracy. And so I wanted to jump over to this point of view. My point of view on all of this is that so here's the same chart, just a little more conceptual. Right now, I've been most of us have been working on this first part of reducing costs with a little bit of a reduction in accuracy. And at least in my mental model, well, first of all, I'd say if this was all we were doing, just this first part, I'd be a little bit uninspired by that because I don't know, it's hard. It's a difficult selling point. It's
and you only economists would be happy you're cost cutting, right?
Right, but it's just saying you can dramatically reduce your costs, and it kind of hurts your accuracy. Okay, I'll just say the second part. In my mental model, I'm also looking forward to this next step of we can also now essentially run larger networks, larger sparse networks that can actually outdo the original one. Seeing this as the first step of a stage of then being able to then
reinvest the savings.
And do better. Another way to say it is I could have drawn, we could even go denser and maybe get better results out here, but this might be prohibitively costly. But now we can actually get to those points because we're over there. So my point of view is this is all kind of the first stage of this process. And maybe for a lot of applications, yes, the first one's valuable, but it's comforting to know that that rounding this curve is also going to be a path forward.
Good. So let's backtrack a second where you're talking about these sparse to sparse. Does someone have a practical way of actually reassigning weights in a sparse to sparse, or reassigning connections to the sparse to sparse?
There's several techniques, and I think Michelangelo and Lucas worked on some. I don't remember if you were. Okay, but there's several different techniques.
Because dense to sparse, you can see, okay, I can rank them all by some criteria, but if it's sparse to sparse, you have no information. But what happens is, I mean, it seems like you have a huge space to explore without a huge amount of guidance.
Right. Yeah. But you can still do it. I mean, you can't guarantee you're going to explore the full space, but there are still techniques to doing better than a static structure.
I have a question. So you maybe wisely said on the x-axis are costs, right? Rather than, you know, number of connections or like, you know, log scale of weights or something. Because in your manuscript, you make this point that, you know, like the way that it works with having a weight decay that, you know, like pushes against the existence of the weight, and then having backprop-permanence that sort of like pushes it forward for the weight to exist.
Yeah.
And then it becomes a balance between that decay and the.
I can bring up the figure you're talking about,
exactly.
just so you're not having
So
to describe it.
that obviously, like you make the point that this obviously this works to reduce the number of weights that exist, but not necessarily directly the cost. In the sense that every weight that you have, if you wanted to actually optimize for the compute cost, right, rather than the weights, the number of weights, which is an indirect way of optimizing compute cost. How would you do that?
Well, you're bringing up, so one of the points I'd make was I show a table that I will show the table, but I'm only going to talk through a little bit. It's up here, almost there. This is a table that goes deep into detail about which layers achieve which sparsity and so on. And one of the points I make in the discussion here is that if you look at number of weights, so this top table, the vast majority of the weights are up in the fully connected layers. But if you look at number of multiplies, the vast majority of them are in the convolutional layers. And and so like the answer to your question you're asking of how do you optimize for multiplies is you prioritize sparsity in the convolutional layers.
Oh, and then you
But you're not doing
weigh
it now?
the.
Right now I'm prioritizing all of them equally.
I see.
And I'm optimizing for number of weights, number of connections. But I make the point in this that when I switch to optimizing for multiplies, I need to use different. So one thing I didn't mention before, the way I'm sparsifying is the permanences are always decaying over time. I just didn't mention that explicitly in this meeting. These permanents are always decaying, and what I'll need to do is make it where the permanences in different layers decay at different rates. I'll prioritize the convolutional layers, and then that'll be the way to reduce number of multiplies.
Right. I'm just thinking. So if you happen to know, right, that you know in the convolutional layer, like a weight will cost you, let's say, 10 times, you know, the amount of multiplies compared to another layer, then obviously does that automatically mean that the layer should be 10 times like to have the decay?
No.
No, right?
No. What it means is that I'm going to have a hyperparameter search, and I'm going to use multiplies as my optimization.
Right.
And then I'm just going to let it set whatever permanence decays it chooses to, and it's going to optimize it for me. My outer loop of my hyperparameter search is going to do all that thinking for me.
Yeah.
Yeah.
Yeah. So it's not intrinsic in the mechanism. It's like externally the hyperparameter tuning.
Yeah.
Right. And then the parameters to tune for are like layer-wise sparsities.
Yes.
Like desired sparsity levels.
Or
that you're looking for.
Technically, I'll tune for layer-wise decay rates.
Right. Since that then sets the sparsity.
So I mean, your sparsity right now is a proxy for some cost function, but so is multiplied as a proxy for some cost function.
Yes.
In the end, the cost function is something that's really determined that we're not even thinking about right yet.
Yep.
Right? We don't know yet. So
Yeah, I guess in one case, the top one optimizes for memory usage.
Yeah.
If you're going to
Yes.
store a compressed version,
Yes.
and this is like computational.
yeah,
Yes.
but in terms of the actual business function cost, we don't really know what that is yet.
Right. I guess what would be cool to see, just to make that little point, is to close that loop, right? If one were to think of that, is to, instead of optimizing to sort of like lower the cost, right? Sort of like immediately reinvest all the savings into, I don't know, additional layers, right? Or like wider networks, and then see what is the, and then you can optimize for accuracy again.
Yeah, I mean, for research purposes, if we're trying to build the biggest, best AI thing that no matter what the cost, that's what's nice about this.
Make
you
it
can also pursue
one
those
thing
things.
that closes on itself, right? Rather than 2 steps.
Of course, I think ultimately in the world of AI or machine learning, that's probably not the thing we're going to optimize for. And that's the way the machine learning world works today. 0.01% better is better. It's like, but in reality, that's not the way the world really works. We also don't really know what is the actual ultimate possible performance metric. Maybe these net networks are already there. Maybe you can't improve them any further. That's just the data is bad after that. Who knows?
Well, that's very much the case for MNIST for sure. You can't improve it anymore.
Yeah.
And quite likely for GSC.
So it does not fool ourselves to think if we can't get better accuracy by going deeper and wider, that's a failure in any sense.
No, but I think it's also incorrect to focus too much on accuracy because there are other metrics that are equally important.
Yeah, I think there's something too. So it's a nice idea, but let's not get down that rabbit hole completely. It's like, let's see if it works, but let's not spend months trying to see if that works.
If you're focusing too much on accuracy on these little things, you're basically fine-tuning for this test set.
And in very small differences in some of these test sets, which really, in a practical point of view, make no difference at all.
So when you do comparisons to other models, other ideas, is this going to develop into a proper paper?
The open question. It could be part of them.
Right. Nicely written. I mean, it's well on your way there. Beautiful.
It's a really good starting point.
I'll highlight one thing.
The language is not quite the way you would write it for a paper.
No, I mean it wasn't intentional.
What paper is this? This is Marcus's write-up.
I mean, I wrote it in the form of I and we and and permanences, and as if people know what a permanence is.
In terms of its content, format, and the charts, everything's all there.
One thing I'll just point out where this was a little bit of a different kind of experiment than we often do. So these x-axis, often when we have an x-axis and a y-axis, and these dots essentially float around. And I defined different sets of parameters to find something that was around this sparsity, find another one that's around this sparsity. So that was a difficult task of a difficult hyperparameter search where I was just choosing all these things to find this cloud of points and to show you the best ones.
I think that's very typical.
Things that were down here. The points that were optimal by some definition of optimal. And that's all I got.
And again, for MNIST and GSC, there's a very high likelihood those things are overfitting to the test set. We can do that.
Sure, maybe, sure. So in the sense that I guess the right thing to do.
The test set is part of your training regime, basically.
I'm curious if that's true.
It is. The way to avoid it is to have an in-between validation set, which we don't have for MNIST. GSC does have that.
Yeah, I did. Yeah, I know.
But
I was too lazy to use
exactly.
it.
So I
can break. We have a tool that breaks that. It's part of the training for validation.
Yeah, but then you'll get lower accuracy across the board.
I'm curious to
know
know.
how you can't do that.
So I'm curious about something. So I look at the speech commands one, and you're looking at almost 2 orders of magnitude reduction over the dense network, and you're looking at 1% reduction in accuracy. That seems really impressive to me. Should I not be impressed by that?
One part where I was lazy here, or where I could have, the dense network is going to have lots of weights that are close to 0. And I didn't do any work to prune those and see if the network still works.
But then it wouldn't be dense anymore.
That's not dense.
I know, but the point is that network is maybe it actually is.
Well, when other people report results on the speech network, do they drop out those those close to 0 ones, or they just leave them all in?
They leave them in. Now, what you could do is have another line that's the pruning line.
Yeah.
Right? If you do different amounts of pruning, how does that compare?
Yeah.
Yeah, obviously not interesting. If I did pruning and I got down to 2 orders of magnitude less weights, then I guess
Then it wouldn't be as impressive.
No, it would not. My excuse.
Yes, your excuse.
Go finish the book.
Thank you, Marcus.
If anyone else has questions or whatever.
Do you remind me how you freeze like there's like for training you have this stochastic component, but for instance, do you still like sample that Bernoulli variable, or is there?
It's an important question, but yeah, I didn't go. Pretty much that's only answered in the code. So
I think you mentioned this before.
yeah. So it's always useful when you have something like this that your inference is still deterministic. So you don't want to sample randomly. And what I found worked best, and I found this months ago, and I've just been sticking with it. I assume it still works best. Is that that there's a what's the best way to describe it? Each unit has, like, I'll just do this. It has like some number of permanences, like theta 1, theta 2, etc. And each of these is a different like Bernoulli variable. If you sum all these thetas, you get the expected number of synapses on this unit. And so what I do is I sum all of these to get its expected number of synapses, and then I select the top k, or rather, like say k equals some. That was a summation. What? K equals summation of like theta, its expected number of enabled synapses, and it's choosing the ones that are kind of the best, so to speak. So that's how that once I did that, I was like, first of all, I was like, oh, this is of course the right way, and I did it, and results got much better. So it is a useful thing.
I think another field is called importance sampling.
Importance what?
Sampling. So figure out which you're going to minimize the number of samples for the most important. What you're saying is these are the ones that have the best contribution in the ratings too. So anyway, I'm just in case you want to explore that's a term that gets used.
All right.
Cool. Matt, I think we can stop this stream.
All right, you're offline. One second. Okay. So hey, thanks for watching. Please hit the like button for me. All you guys, 14 people watching right now or whatever. It's helpful to get likes on the videos. And I just want to let you know that I'm going to be not streaming for a couple weeks starting on the 19th because I've got a medical thing I got to deal with. But I will be back hopefully soon and back to streaming as soon as I can. And I will put on YouTube eventually. Sound good? Thanks guys, thanks everybody, thanks for watching. I'm going to cut the stream. Take care, see you on the forums. Go to HTM forum, join HTM forum if you want to chat with any of us.